What does the area of a velocity versus time graph represent? That's what we're going to understand by the end of this lesson, and it's a very profound idea. We're going to be looking at the area underneath graphs or above graphs, and they actually mean something. So let's get started. I'm going to start off with a position versus time function. So let's say I have x equals 3 meters per second times time, and then we'll plus 5 meters. Okay, so this is a position versus time function. And there's some information here. We know where to start. We know how fast we're going, and we know what direction we're going. We're going in the positive direction for this. And we can figure out a lot of other things about it. And one of the things we can do is draw a position versus time graph. And let's do it for 5 seconds. And again, to scale the vertical scale, I just need to 5 seconds. So 3 meters per second times 5 seconds is 15 meters, plus 5 is 20 meters. So let's go 10, 20, and then we'll do 5, and then this will be 15. So 5, 10, 15, 20, and then I'll go ahead and put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20. And so go ahead and use your graph paper to do this. I'm just freehanding this. This is position in meters, time in seconds. So let's graph it. We're starting at 5 meters. And now I could, if I wanted, I could go every second, but I'm just going to graph it. So I know that at 5 seconds, I'll be at 20 meters. Connect those two. Okay. So this is one way to represent the motion of an object. This is another way of representing its motion with a graph. We can also represent its motion with a velocity versus time graph. And I'm going to do it as a kinematic stack. So 1, 2, 3, 4, 5. I draw it directly underneath. And then this position axis just comes down. We'll make it now the velocity axis. And what's true about the velocity here? It's the slope of this line, so it's a constant, and we know that it's 3 meters per second. So 1, 2, 3. And it's the same for at each time. That's what we mean by constant. Okay. So now, let me ask you this question. We're going to use both these graphs here to do this, to answer this question. What is the total displacement for the whole thing. What's the total displacement here? Well, what do I mean? What do I mean by displacement? Let's use this graph to do it first. Yeah. So what is displacement? What's the variable name I use for displacement?
X final minus X initial.
Okay. Okay. I'm going to call that delta x, and then delta x is equal to x final minus x initial. Right. That's the definition for displacement. And now, what's x final? What's the final position here? Well, on the graph, I look over, and it's 20. Minus my initial position. Now, this is for the whole 5-second interval. Well, it started at 5 meters. So I can say that the displacement equals 15 meters. That's how much I changed my position, right? If I start at 5 and I end up at 20, I changed by a positive 15. Simple, right? Everybody got that? Okay. But there's a way of getting that from this graph as well. And let's think about this. I mean, if I told you, let's not even look at this problem. What if I told you I was jogging along a street and I was jogging at 3 meters per second, which is that's a jog. You're jogging at 3 meters per second, and you do that for 5 seconds. How far are you going to go while you're jogging for that 5 seconds? You know, and how did you get that 15 meters? What did you do? You multiplied, right? Because you said, oh, I'm going 3 meters per second. That means every second I'm going 3 meters. But I do it for 5 seconds, so that 3 meters times 5 is 15 meters. That's the mental process you went through. And I want you to think about stuff like that. How did I know that? Well, but now look at this graph. Where is the 15 meters in this velocity graph? Well, think about it. Let's look at the first second. How far did I advance forward in the first second? 3 meters. So let's look at this. And look, what if I went 1 meter per second for 1 second? Or 2? Or 3? I'm going to break this up into little squares. How many little squares are there? 15. What's going on? Okay, I'm going to look in detail at one of these little squares. Just randomly pick this one right here. So I'm going to redraw it. This little square. It doesn't have to be a square, it can be a rectangle, depends on how you scale it. Now, how do you find the area of a square? Length times width, right? Well, look at this. What is the length of this square? 1 second. Wait a minute. A second isn't a length. It's not 1 meter either. It is 1 second. Okay, here's my point. I'm trying to confuse you. This is a length from here to here. I mean, it's physically a length. But we're using that length to represent something that isn't a length. We're using this length to represent time. You see that? Now that's pretty abstract. Okay, but you need to understand that. This this length is not a length. This length is representing 1 second of time. Now what about this length right here? It's one, what it represents a one what? Yeah, look at the vertical axis, 1 meter per second. So again, we're using a length, a vertical length right here to represent something that is not a length. Now let's do the math. Let's get the area in quotes. Well, it's the height times the width. Now what is this equal to? 1 meter. 1 times 1 is a meter, but then if you look at the units, the second cancels the second here. A second divided by a second equals 1. Anything divided by itself is 1, and you multiply or divide by 1 and you just get 1, or get the thing, and so there we go. So here's what has happened. This is an area, right? An area. And when you look at an area, like if you want to know the area of the floor, we would measure the floor and multiply the width times the length of the floor, and we would get an area maybe in square feet, right? Or square inches or square yards, whatever, square meters, whatever you're using. And that would be true area. Okay? But this area does not represent area. This area in my graph like this represents something that isn't area. What does it represent?
Or velocity.
Well, this length represents time. This length represents velocity. But what does this area represent?
Acceleration. Distance.
Nope. What is this?
Position.
It's not position. Okay, if I'm walking at 1 meter per second for 1 second, I have changed my position by 1 meter. Yes? What do we call that? Displacement. So this is 1 meter of displacement. But I wasn't walking at 1 meter per second. I was walking at 3 meters per second, or jogging at 3 meters per second for 5 seconds. And so instead of, I could count the squares. That's 1 meter, 1 plus 1 meter, plus 1 meter, plus 1 meter, and so on all the way through. And there would be 15 meters. I could do that. That's a little tedious to draw every square and then count them all. Or what else could I do? I could say, well, 3 meters per second times 5 seconds is 15 meters. And so I can do that. So delta x is going to be equal to the height of my big rectangle times the width, which is 5 seconds. And that gives me 15 meters. Same answer I got by using the position graph. Just used it a different way. So here's the big idea here. The area of a velocity versus time graph represents velocity. I'm sorry. I'm getting ahead of my. I'm trying to think ahead, and then I end up being stupid. The area of a velocity versus time graph represents displacement. Okay. Okay. So here we've got two ideas here. The slope of a position versus time graph represents velocity. The area of a velocity versus time graph represents displacement. And that is, that's a very profound idea. It's kind of, in more sophisticated mathematical terms, that's one of the fundamental theorem of calculus, which you'll learn about in your calculus class. But it's easy to see here, I think. Okay, this is a very concrete example of that. Now, let me ask you another question. What is the displacement from t equals 2 seconds to 4 seconds? So like within there, I mean, what's the displacement going to be within there? And let's use the position versus time graph to do it. Well, at 2 seconds, what is my position? Well, if I go, let's see, I'm starting at 5 and I go up by 3 every second. So 1, 2, 3, 1, 2, 3. So I think at 2 seconds I'm at 11. So I'm going to put a dot right there. And then at 4 seconds, well, 1, 2, 3, 1, 2, 3. What's that, 17? So here's my displacement from 11 to 17. This is 17 meters. This is 11 meters. Those are my positions. Let me zoom in a little bit so you can see that in the back. You see what I did there? At 2 seconds, I'm at 11 meters, and at 4 seconds, I'm at 17 meters, and so that gives me a delta x is equal to 6 meters. Does that make sense, everybody? So that's using your position versus time graph or your mathematical model. You can use both to do that. But you can also do the same thing using your velocity versus time graph. Oh, so we got 17 meters minus 11 meters. Those my final position minus my initial position. That's 6 meters of displacement. Now, if I use my velocity versus time graph, well, the area of a velocity versus time graph represents displacement. But instead of the whole thing, I'm just going to go from 2 seconds to 4 seconds. And I'm going to show that just by shading it in. Here's 2 seconds. Here's 4 seconds. So I'm just going to shade it in. And what do you notice about this? How many little squares are in there? 1, 2, 3, 4, 5, 6. 6 meters. Each square represents 1 meter of displacement. And so now I've got 1, 2, 3, 4, 5, 6 meters of displacement. So I'm just going to say, hey, you know, from looking at that, delta x equals 6 meters. And you can go, okay, 2, like 1, 2 times 3, 1, 2, 3. 2 times 3 is 6, and it's 6 meters of displacement. I mean, there's lots of ways of looking at this. But I do want you to know how to figure out what the displacement is using the mathematical model, using the position versus time graph, and now using the velocity versus time graph. Okay. Now, keep saying this, but I hope is this clear to everybody? Okay. And I'm telling you, if it's clear to you right now, good. Hold on to that, because this is important. This is really profound. And it will, when you get into more advanced physics and more advanced calculus, and you start losing, you get lost in the fog, like what's going on. If you go back to this basic idea, it'll help. You go, okay, what's really going on here? And this will help you do that. Now, what's next? Okay. Where did I put my notes? I'll just have to go on memory. What if I told you this? A jogger is moving with a constant velocity of negative 4 meters per second for 10 seconds. Okay. So I want to look at. Oh, wait a minute. Oh, wait. No, I'm sorry. Not for 10 seconds. And actually, this doesn't make sense for a jogger. So how about we'll do. We'll just make it for 4 seconds. Then changes direction and runs at 6 meters per second for 6 seconds. Okay? Yeah, that's what I meant to do. Misplaced my notes, so I'm going on memory now. Oh. Well, I changed the numbers a little bit. Thanks, though. All right. Well, let's draw. So this is somebody who's maybe not a jogger, maybe like a football player or something, is running one direction really fast, and then on a dime changes direction and runs the other way even faster. Now, this isn't technically possible to instantaneously change your speed like this. It would shatter every bone in their body. But that's okay. It's just a little, it's just a pretend football player. All right. So let's draw the velocity versus time graph here. Now look, I got a negative velocity here now. So here's velocity and here's time. Now how much time do we have here? 10 seconds, right? Total of 10 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then at first, they were going -4 and then +6. So I want to go 2, 4, 6. And then over here, -2, -4, -6. So it says -4 meters per second. So let's graph this and see and figure out what it means. So they're going -4 meters per second. So that's right here. For how long? 4 seconds. So that's a constant velocity. And then somehow, by some miracle of technology, they instantaneously change directions. And now they're going positive like this. Yikes. All right. Does everybody get that? Right. Now, here's one mistake. Some people like to make the squares. And I want to ask, what is the total displacement? What is the total displacement here? Well, let's look at this first part. If you were running at -4 meters per second for 1, 2, 3, 4 seconds, what's your displacement? 16. So this will be our first delta x. Delta x will be equal to 16 meters. But in what direction? To the left, right? Because your velocity is to the left, so your displacement's to the left. Well, what direction? How do we say to the left in math? We put a negative here. That is, our displacement was 16 meters to the left. Or whatever we're calling the negative direction. We start off going the negative direction. And then what happens? We turn around and we start running the positive direction. So what's the area underneath this graph represent? Careful now. Let's think about the area of this rectangle.
36.
And how did you get 36? 36 meters, right? Well, we're going 1, 2, 3, 4, 5, 6. 6 times 6 is 36. By the way, if you scale it this way, watch what will happen. Some students will make squares like this. And they'll say, oh, 1, 2, 3, 4, 5, 6, 7, 8. It'll be 8. Where are they going wrong? Well, what is the height of each square? Yeah, -2 meters per second. So each square is worth 2 meters of displacement, not 1 meter of displacement. In this case, negative. Okay? Okay, so what was the total displacement?
20 meters.
Yeah, so we're going to say delta x should be equal, the total, we'll call this delta x1 and this delta x2. So we went 16 meters in the negative direction, and then we went 36 meters in the positive direction, and so -16 plus 36 is 20 meters of displacement. Now we could try to draw a position versus time graph for this. And then we'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Try to keep that all lined up. Time in seconds. Make sure you put the units on there. But let's see, how are we going to scale this? Well, I need to know where to start. Where do I start? Yeah, we could start at the origin. Why not? Or should I say x naught? All right. All right. That was a knee slapper. All right. So at 4 seconds, we know we've gone down to negative 16, and then we're going to go up 36, but we'll end up at 20. So we need a scale here. So I'm just going to go 5, 10, 15, 20, 5, 10, 15, 20, negative 5, negative 10, negative 15, negative 20. Now, I'm very fast at this.
Bless you.
Thank you. Oh, never mind. You'll get faster at drawing these graphs the more you do them. So I know that at 4 seconds I'm going to start here. Now, you don't have to start there. You can draw the graph anywhere. You can start it anywhere you want. But sometimes I'm just going to say, hey, let x naught equal 0. You can just say that. Let's just start at 0. And then at 4 seconds is where we have a change. And I know that after 4 seconds, I've gone to 16. So here's 16 right here, negative 16. And I know that the velocity is constant, so I've got a constant slope. And then I know that at 10 seconds, I'll be at a total displacement of 20 meters from where I started. I'll be at 20. And there we go. There's our position versus time graph. Hey, when was my displacement 0?
12 before 7 seconds.
So 6, so we want to go back 16. So here we go, 6, 12, 18. So like somewhere between 6 and 7 seconds. Oh, look at that, between 6 and 7 seconds. This crosses the 0 where we started. That's kind of cool. So I can take the position versus time graph, look at the displacements, use that. Oh, by the way, what is, look, see this is positive 36? Well, look at this. From here to here, that's 36. You know, if you go, you know, x final minus x initial, based on what I did, x final was 20 meters minus x initial was negative 16 meters. What is 20 meters minus negative 16? 36 meters of displacement from here to here. So there's a couple of ways you can look at the area underneath the velocity versus time graph is displacement. And you can use those displacements to draw a position versus time graph, except you always need to know where to start. On the test, you're going to have something like this on a test. I will tell you where to start. If I give you a velocity versus time graph, and then a position versus time graph, I'll tell you where the starting position is, so you can draw the graph properly. What if I told you that x naught was going to be equal to 5? The graph would look the same, except that it would be parallel. It would look something like this. You don't have to draw this, because it'll just make your graph messier. But it would look like this. It would be the exact same graph, just shifted up. In your AM class, do you ever do any shifting of functions? Shift it up and down? Yeah, you probably did. All right, never mind. So everything just gets shifted up by 5. But we didn't do that, so let's just erase this. All right. So just to review, we have we can draw, if I give you a function, you can draw the position versus time graph. You draw the velocity versus time graph from that based on the slope here. But the area underneath this graph, or I say underneath in this case, but above, the area of the graph, the area is, let's go back and look at this. if your velocity is negative, the area of the graph goes from where the graph is to the t-axis. And up here, it's from where the graph is to the t-axis. So here's positive area, negative area. So the area underneath the velocity versus time graph represents displacement. You can have negative displacement or positive displacement, depending on what your velocity is. And then to get the total displacement for the whole thing, if you have two different velocities, you just add them together. Make sense? Any questions? Oops. Okay. That is all.